Today we are going to discuss some basic limit laws. So we'll start with the very basic one, the first one, which is for any constant c, limit x approaches c of k is equal to k. For example, if x approaches 5 and I have the k is 10, then that 10 doesn't care for what x is or where x goes. That 10 is going to remain 10 because it doesn't depend on the x. Okay, so limit x approaches c for the k would be equal to k. And another example for the second law here, limit x approaches c of x is equal to c. So if I have limit x approaches 5 of 5, that would be equal to 5. I'm sorry, that would be here. Limit x approaches 5 of x. Limit of x when x approaches 5 would be 5. The next, suppose limit x approaches c f of x and limit x approaches c g of x exist. So this is the first condition, that both of these individual limits exist. The following properties hold true where c is a real number and p and q are integers both greater than 0. So first one is the sum law. If you are trying to find out the limit x approaches c of sum of two functions, you can find the two separate limits and add them. Constant multiple law, limit x approaches c, k f of x, k is the constant, multiplied with the function. We can pull the constant out and find the limit and multiply the limit with the constant. Next is the product law. If you're trying to figure out limit x approaches c of f of x times g of x, then limit x approaches c f of x times limit x approaches c g of x. We can find the individual limits and then find the product of those limits. Next, we have quotient law. Remember, whenever we are talking about the quotient, we never want our denominator to equal 0. So if limit x g of x approaches c should not equal to 0. The denominator should never ever equal 0 because that makes our function undefined. So if you're trying to find limit of a quotient, we can find the limit of numerator and limit of denominator and then find quotient of those two limits. Next, we have the power law. So if you're trying to figure out limit of a function raised to a power, we can find the limit of the function and then raise to the power n. Fractional power with even denominator. So if we have a function greater than 0 and q is even, so if we have p over q where q is even and it's reduced to the lowest terms, we can, for the law limit x approaches c f of x raised to the power p over q, this is a rational exponent. We can take the limit and then raise it to the power p over q, rational exponent, as long as q is even. Okay, limits of polynomial and rational functions. Very important. Limit properties to remember, that if you have a p of x and q of x are polynomials, quickly to help you remember, polynomial is product terms where you have a product of numbers and variables, and then you can have multiple terms in there. Some are difference of product of numbers and variables. Okay, for example, the polynomials, they cannot have fractional exponents. They can have fractional coefficients but not the fractional exponents. One example of a polynomial is no negative exponents and no fractional exponents. X squared plus 3x, it's a polynomial. X to the power negative 1 plus 5x squared, not a polynomial. So polynomials don't have a negative exponent and they do not have fractional exponent. Okay, they can have fractional coefficients but no fractional exponent. 3 over 2x squared plus 5x, yes, polynomial. Okay, all right, so provided limit x approaches c p of x is equal to p of c. This is very important. So if we have a polynomial, then we can simply evaluate the polynomial at c. That means every single x gets replaced by c and we can evaluate that polynomial. We'll see examples in a minute. Next, provided q of c is not equal to 0, the limit x approaches c of q of x is not equal to 0, then when you're trying to figure out the limit of the quotient p of x over q of x, we can just evaluate the numerator and denominator at x equals c. That means every single x gets replaced by c and we simplify it. Another note that sum law and the product law works for any number of functions, not just two functions, okay? Also keep in mind, as long as the function is continuous, which will be your polynomial and rational functions. Rational functions are continuous as long as the denominator is never 0. Polynomials are always continuous. As long as the function is continuous at x equals c, we can just move the limit inside. Means we can plug c in for x. Here we're going to look at several examples. Be careful when you have a denominator. We need to be sure that the function is continuous at x equals c. That means if you have a polynomial, then no need to worry about continuity. But if you have a rational function, make sure your denominator is not 0 at the point where you're trying to evaluate the limit. Let's see some examples. The first one, we have limit x approaches to 29 x squared minus x to the 5th power. So here we are going to plug in the, first of all, it's a polynomial. X squared minus x to the 5th power is a polynomial. It might look scary as of now, but we don't need to evaluate that or expand that polynomial. So that should be not an issue. We're just going to go ahead and plug the x as 2 in here because this function, the function we are dealing with, is continuous at x equals 2. It's a polynomial. So if you're evaluating the limit of a polynomial, you can go ahead and replace the x's by the number c. In this case, the c is 2. So it's going to be 29, 2 squared minus 2 to the 5th power. 29 times 4 minus 2 to the 5th power. 29 times 2 to the 5th power, which is 29 times 32. And that would be 928. Right, another example, limit h approaches 0, 3 over square root of 16 plus 3h plus 4. In the second example, first of all, if I replace h by 0, I don't get 0 in the denominator, so the function is continuous. If you look at the previous law we just talked about, as long as q of c is not equal to 0, we can just go ahead and replace the x's by c's, okay? And in this case, q of c, which is the denominator, q of c is not equal to 0, because if I replace h by 0 in the denominator, then my denominator is not going to equal 0. If I replace h by 0, I would be getting 16 plus 0 plus 4, which is square root of 16 plus 4, which is 4 plus 4, which is 8. So my denominator turns out to be 8. It's not equal to 0. That means I can just go ahead and evaluate the numerator at h equals 0, which numerator doesn't care for h because there's no variable in there. But in the denominator would be 16 square root 16 plus 0 plus 4. 3 over square root of 16 plus 4, which is going to be 3 over 4 plus 4, and that's 3/8. That's going to be our limit. Next example, x approaches 1. Again, be careful. We have a rational function. And we just said as long as the denominator is not equal to 0, we can just go ahead and plug that c value into the numerator and denominator separately. So let me quickly check. 3 times 1 plus 2 is not equal to 0. So that means q of c is not equal to 0. That tells me that it's okay. I can go ahead and plug in 1 for the x's. So that turns out to be negative 3 plus 1 minus 7, which is negative 10 plus 1. That's going to be negative 9 divided by 3 times 1 is 3 plus 2 is 5, negative 9/5. Example number 4, again, I want to see if q of c is, so that's going to be q of 3. This is my p of x and this is my q of x. Q of 3 would be square root of 4 times 3 minus 3, which is 12 minus 3, square root of 3, square root of 9 is 3, and that's not equal to 0. So q of c is not equal to 0. That means I can go ahead and evaluate the limit by, this is going to equal p of c divided by q of c, which would be negative 7 times 3 divided by square root of 4 times 3 minus 3. That's negative 21 divided by not 9, negative 21 divided by 3, and that's equal to negative 7. So there's I'm just using basic limit laws where we have some product polynomials, rational functions, the laws that we just talked about. Okay. Next, limit x approaches 3/2, 4t squared plus 8t minus 5 raised to the power 3/2. Okay, so let's see, this is 3/2. It's a radical function, but it's a square root radical function raised to the power 3, and it's continuous at 3/2. Okay, so I'm going to go ahead and replace every single t by 3/2. And then simplify it using the calculator. 4 times 9 over 4, which would be just 9. And that would be 4 times 3, 12, minus 5. 9 plus 12 minus 5, raised to the power 3/2. That is 12 minus 5 is 7. Plus 7 is 16 raised to the power 3/2, which is square root of 16 to the third power, 4 to the third power, and that's going to be 64. So that's what this limit turns out to be. Next, limit x approaches 8, 3x to the power 2/3 minus 16x to the power -1. It's a rational function, so I need to make sure that my denominator is not 0. So if I write it slightly differently, my denominator is not 0 at the value c. That's all I care for. Denominator can be 0 at the other points, other values of x, but just at that value, it should not be 3x to the power 2/3 minus 16 over x. Okay, now x approaches 8, and this denominator is fine as long as it will be troublesome when x approaches 0, but as long as x is approaching 8, there's no issues with this function. It's continuous. So 3x to the power, I'm going to replace the x's by 8. 8 to the power 2/3 minus 16 over 8. 8 to the power 2/3, which is cube root of 8 raised to the second power. That's the same thing here. Cube root of 8 raised to the second power minus 2. So cube root of 8 is 2. Root 2 raised to the second power is 4. 12 minus 2. So this limit turns out to be 10. Okay. Go ahead and evaluate the next two limits and check. The first one should be 39. The second one should be 1. Double check your work. Okay. Now, one quick note. Remember, the basic limit laws, the ones we just talked about, only apply as long as both individual limits exist. As long as the limit x approaches c f of x exists, it can be 0, but it should exist. And limit x approaches c of g of x exists. Here's some examples. So let's look at example number 7. Can the quotient law be used here? Can we use the quotient law here? Now, the limit, so here, limit x approaches 0, sine x over x. So this turns out to be, we said the quotient law only works. So when we talked about these rules, we did say that quotient law only works as long as the limit g of x is not equal to 0, where g is your lower function. And in this case, my limit, so this is f of x is sine x, g of x is x, limit x approaches 0, g of x is equal to 0. Thus, quotient law does not work here. We cannot use the quotient law, does not apply. Quotient law does not apply over here. Okay, next, given f of x is x and g of x is x to the power -1, can we find this limit? So let's see. If I go ahead and I say limit x approaches 0, x times x to the power -1, x times, because this is going to be limit x approaches 0, x times 1 of x, these will cancel, and I'm left with limit x approaches 0 of 1, which will be 1. Does that look right? Is that correct? Notice that limit x approaches 0, x exists and is equal to 0. But the limit x approaches 0, 1 over x does not exist. Both individual limits should exist, only then the product law works. So product law only applies if both individual limits exist. If individual limits exist. Only applies if individual limits exist. If individual limits exist. That's what we started with, that both individual limits should exist, only then the product law works. If individual limits do not exist, then product law cannot be used. Okay, that would be all for this video. In this video, we just talked about some basic limit laws.